All right, we're beginning chapter 6 on relations and digraphs. So this is following our discussion on functions. So relations are very similar to functions, except they are less restrictive. Okay, so our first section is just an introduction to what a binary relation is. So a binary relation, here's the definition. So a binary relation, we'll just denote it with the capital letter R, between two sets. So A and B are the two sets. Okay, just like a function, it is a subset of the cross product of A and B. So remember, when you take the Cartesian product A and B, you'll get ordered pairs where the first element in the ordered pairs from A and the second one is from B. Okay, and we call R a binary relationship, a binary relation, because the Cartesian product is just two sets. Okay, the A and B may or may not be equal. Okay, we'll look at examples of both. And then the fact that the ordered pair AB is in the relation, part of the relation, is just denoted with A and then a capital R and then a B. Okay, that just means A is related to B. All right, so very similar to functions, like I said before, but there's no restrictions where, like, for each A there has to be one B, like, so that it's a function. So none of those rules. You can have as many B's related to A as you want to, and as many B's related, okay. So it doesn't have to be onto, nothing like that. Just any kind of relation. All right, so if we have the two sets, okay, essentially like our domain and our target, okay, if they're finite, then there's lots of different ways that we can represent them. So certainly as a list of ordered pairs, where we just list all the ordered pairs that are in the relation. We can also use what's called an arrow diagram, and we saw this for functions as well, where we list all the elements of A, and we list the elements of B, and then we put an arrow from one to the other if there's a relation. And we also have a new relation that we didn't see for function, that's a matrix representation, so we'll look at that. All right, so let's just look at an example. So let's say I have the set A and it contains 2, 3, 5, and 7, and the set B that contains the integers 1 through 10. And then we define a relation that A is related to B if A divides B. Okay, so let's go ahead and look at the three different representations that we could have for that. Okay, so first of all, we could do it as a list of ordered pairs, or a set of ordered pairs. Okay, so let's just go through here. Okay, well, what is 2 related to? Well, 2 is related to another number B if 2 divides it. So let's think about the thing that 2 divides. All right, so 2 divides, well, it doesn't divide 1, but 2 divides itself. 2 divides 2. Okay, 2 doesn't divide 3, but 2 divides 4. Okay, 2 doesn't divide 5, but it does divide 6. In fact, 2 divides every even number, right? So we would also have 2, 8, and 2, 10. Okay, so those are all the numbers that 2 divides, so that's everything that 2 is related to. How about 3? Well, let's see. 3 divides itself, and 3 divides 6, and 3 divides 9. That's everything that 3 is related to. And then 5, well, 5 divides itself, and 5 divides 10. That's everything that 5 divides. And then 7, well, 7 only divides 7. Okay, so those would be all of the ordered pairs in the relation. If we wanted to write those out, I could pick out one of these, like 3 and 6, and I could write that as 3 is related to 6. Okay. So this is just an example of the notation. And that would be, we could write 7 is related to 7, or 5 is related to 10. So we could use that relation as well. But this ordered, we get all of that from the ordered pairs. Okay, we could also use an arrow diagram where we first of all would list, all right, well, let's list 2 here, and then we would want to list all the elements eventually over here. But so it's not a mess. Let's just go, all right, well, 2 is related to 2. So we'd have that in there, and 2 is related to 4. And 2 is related to 6. And 2 is related to 8. And 2 is related to 10. So we would have all of those in there. So notice this is definitely not a function, okay, because we've got multiple arrows coming out of 2. It's related to lots of things. So you can clearly see the difference between a function here. Okay, and then we have 3. Well, 3 is related to 3. We haven't written 3 there yet, so let's put 3. And 3 is related to 6. That's already there, so let me put that in. And 3 is related to 9. Okay. 5 is related to 5, as well as 10. And then 7 is related to 7. Okay, we've listed all of A. Let's see, we haven't listed 1 yet, so maybe I could just put 1 up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 are all listed, so all of B is listed here. So this would be an arrow diagram for the relationship. So everything that's that's represented here is also represented over here as well. And then finally we have the matrix representation. So with a matrix, okay, what we're going to do is create a matrix where A will represent, I'm just going to label, I'm going to have 2, 3, 5, and 7. So the rows of the matrix will be associated with the elements from A, and then the columns of the matrix will be associated with the elements of B. So I'm going to put these up here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so I'm going to have a 4 by 10 matrix. 4 rows, 10 columns. And then when I go to each row column pair, okay, the entry in that row column pair will tell me whether that row is related to that column. Okay, so if I go to like 2, 1, the entry in matrix element 2, 1, okay, will be a 0 if they're not related, and a 1 if they are related. Sort of like a 0 is false and a 1 is true. Okay, so is 2 related to 1? No, it's not. I put a 0 there. Is 2 related to 2? Yes, it is. And then no, yes, no, yes, no, yes, no, yes. 2 is only related to the even numbers, right? Okay. And then if you think about 3, well, 3 is only related to multiples of 3, which are itself, and 6, and 9, so everything else will be 0. And then 5 is only related to itself and 10. Nothing else, so everything else will be 0. And then 7 is only related to itself. That's the only thing it divides. Okay, of course it divides 14 and 21, but those, we aren't considering those. Okay, so that would be the matrix representation of the relation. Okay, and once again, if we wanted to write out all the pairs that are related, we'd just go look for the ones. Here we would get, like, 5R5 or 5R10 or 3R6. Okay, so the same information is represented in each of these. They're just different convenient forms that we can look at depending on our context. If we were trying to program something, it's probably easier to deal with something like a matrix, or a graph representation than just a big old list of ordered pairs. Okay. So oftentimes we have a binary relation on just a single set, so where A and B are actually both the same set. So a binary relation on a set A, so on a single set A, it's just it's just a subset of A, Cartesian product with A. So ordered pairs where both of the elements of the ordered pair come from the same set. Okay, and then in this case, A is just called the domain of the binary relation. So it's so both of the sets are the same. That's called the domain. Now this is a special case, and the arrow diagram, we could go and draw an arrow diagram like this, where we have the set A listed here, and then we have the set A listed again. But that kind of complicates things because they're exactly the same number, or the same elements. So rather than listing them twice, we just list them once, and then we just draw an arrow to the elements that are already listed there, if that makes sense. We'll do an example, so hopefully that will be clear. Okay, but there's no reason to list everything twice, because that just makes the graph or the diagram, the picture. If I have 2 listed twice, 3 listed twice, 5 listed twice, 7 listed twice, whatever, it just makes it too big when I know that I'm going to have there's a 2 on both sides, so rather than repeat it, I'll just draw an arrow one time. Okay, so let's look at an example of this. So we've got a set A, 2, 3, 4, and 5, and A is related to B if 2 divides the product of A and B. Okay, so basically if A and B have an even product, right? So 2 divides only even numbers. Okay, so rather than listing every number twice, we'll just list 2, 3, 4, and 5. And we might just go ahead and list it out like 2, 3, 4, and 5. Notice they don't have to be. It doesn't have to be in a single column. Sometimes it's easier to draw if we kind of spread them out rather than put them in a straight row. All right, so let's go through. Okay, is 2 related to 2? Because we have to consider every single pair of elements. So A, so 2 is in A, 2 is also in A, so that's one of the ordered pairs that I need to consider. All right, so is 2 related to itself? Well, 2 would be related to 2 if 2 divides the product, 2 times 2. Well, certainly it does. Okay, 2 divides 4, so 2 is related to itself. So the way that we would denote that is we would say, okay, well, 2 is related to 2. So we would draw an arrow from 2 ending at 2. Okay. Does 2 divide 3? Or sorry, is 2 related to 3? Well, 2 is related to 3 if 2 divides the product of 2 and 3. Well, sure, it divides. So I would do that. 2 is related to 4 if 2 divides the product of 2 and 4. It does. Okay, and clearly 2 has to divide 2 times 5 as well, because 2 is one of the factors. Okay, so 2 is related to everything in the set. How about 3? Is 3 related to 2? Well, certainly 3 is related to 2. Okay, and so I'm going to put, so notice, okay, just because I have an arrow going from 2 to 3, okay, does not mean I will always have an arrow going from 3 to 2. These are 2 different, okay, edges here. So we talked about a graph before. We did a proof about the number of vertices and edges on a complete graph or something. So we talked about, eventually we're going to call 2 a vertex, and 3 a vertex, and 4 a vertex, and 5 a vertex. And this is a special kind of graph called a directed graph. Okay, because the edges all have a direction, and the edge that goes from 2 to 3 is a completely different edge than the edge that goes from 3 to 2. It's directed. So maybe a little note here that this edge, 2 to 3, and this edge, 3 to 2, These are different, called directed edges. Okay. And we'll see, especially in these relations, just because we have one of these doesn't mean that we'll have the other one. Okay. All right, so we decided 3 was related to 2. Is 3 related to 4? Well, 3 will be related to 4 if 2 divides the product 3 times 4. Okay, and it does, because 3 times 4 is 12. 2 divides 12, so 3 is related to 4. Is 3 related to 5? Okay, well, 3 times 5 is 15. That's not an even product, so it's not divisible by 2, so 3 is not related to 5. Okay. What about what's 4 related to? Well, 4 is an even number, so you can probably pretty quickly see that the product of 4 and any number will be an even number, and 2 will divide it. So 4 is definitely related to 2, it's related to 3, it's related to itself, and it's related to 5. Okay, and then 5, okay, well, when will we have an even product with 5? Well, only when it's being multiplied with another even number. So 5 is related to 2, but it won't be related to 3, and 5 is related to 4. Okay. So that would give you the digraph representation of the relation. So one thing to note here is that an element that is related to itself is indicated by an edge or an arrow that's called a self loop. Okay, so this right here is a self loop. That indicates that 2 is related to itself, and this is a self loop indicating that 4 is related to itself. But notice that 3 is not related to itself, 5 is not related to itself. There's no self loop here. Okay. Okay, so let's kind of get a little bit of practice of going back and forth between the different kinds of representation. So right here we have a matrix that represents a relation on the set 1, 2, 3. That's the domain. Okay, so just really quickly, I'm going to kind of note this is like 1, 2, 3. And that relationship is to the same set 1, 2, 3. So we also have that up here. So think of, you know, if this one right here is saying that 1 is related to 1, this one is saying 1 is related to 2, etc. So we would like to represent the relation as a set of ordered pairs. Okay, so convert the matrix to a set of ordered pairs, and then we want to convert the matrix to an arrow diagram. Okay, so let's go for ordered pairs first. All right, so we can just go across the rows one at a time and add an ordered pair for each one that we see. Okay, so this one means that 1 is related to 1. And then this one means that 1 is related to 2. There's no relation here, no relation here. This one means that 2 is related to 2. This one means that 2 is related to 3. And then this one means that 3 is related to 1. Okay, there's no more 1s, so notice that the number of ordered pairs should match the total number of 1s. So there's 1, 2, 3, 4, 5 1s, and 1, 2, 3, 4, 5 ordered pairs. Okay, now let's look at the digraph. Okay, so once again, we'll just take 1 and 2 and 3 and just write them out. And then we could either go through the ordered pairs or go through the matrix. Since we were given the matrix, let's go through the matrix. So this one represents 1 is related to 1. That's a self loop. This is 1 is related to 2. This one is 2 is related to 2. That's a self loop. This is 2 is related to 3. And this one is 3 is related to 1. Okay. And for the digraph, the number of edges that we see, the directed edges, should be the same as the number of 1s. So we remember we had 5 1s, and if we count the number of directed edges, we have 1, 2, 3, 4, 5. Okay, so in each of these we have 5 pairs that are related. So that's a good way to check that you've done it correctly. All right, in the next one, let's look at the digraph, the directed graph, and then from that we'll come up with the ordered pairs and the matrix. Okay, so well, I guess we'll do the matrix first. So let's do the matrix first. Okay, so the matrix, well, we've got 1, 2, 3, 4 elements in the domain. And so we know that we're going to have a 4 by 4 matrix. Okay, and I find it helpful to just write the elements that are in the domain along the rows and columns so that I can remember what each matrix cell represents. Okay, so if I look at, let's just start with 1 and go across this row. What is 1 related to? So we need to look at the arrows that are going out from 1. Okay, so here's an arrow going out from 1 to 3. Okay, so that's in there. And I'm just going to put a little check here to denote that I've caught that one. All right, and then I have an arrow coming out from 1 to 4 there, so I've caught that one. Okay, this one is an arrow coming in, this one is an arrow coming in, this one is an arrow coming in. So this row right here should only represent arrows going out from 1. Okay, so there's no arrow out from 1 to 1, and there's no arrow out from 1 to 2. Let's look at 2 next. Okay, I only want to look at arrows going out of 2. Okay, well, there's an arrow going out of 1. There's an arrow going out of 2 to 1. We've caught that one. And there's an arrow going out of 2 to 3. All right, so taking care of all of those. No arrow going out from 2 to 4. All right, moving on to vertex 3. Okay, we've got this self loop here, out from 3 back to 3. So we're taking care of that one. And there's one that's going from 3 to 1. And that's all the ones that are going out. There's this other arrow, but this one's coming in. Okay, so neither of these. And then finally, let's see, 4. Is there an arrow going out from 4 to 1? Yes, there is. Take care of that one. From 4 to 2, no. 4 to 3, yes, there's one there. Then no self loop from 4 back to itself. Okay. And so maybe we should check really quickly. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 ones in our matrix. We should have 9 edges. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. Okay, so they should match up. And finally, let's look at the ordered pairs. Okay. And it might be easier to keep track of them from the matrix now that we've checked them all off, so we don't have to check them off again. So let's just go through the matrix. All right, so 1 is related to 3, and 1 is related to 4 for these 2 ones. And then if we go across the row for 2, 2 is related to 1 and 2 and 3. So 2 is related to 1, 2 is related to 2, 2 is related to 3. And go across the next row, 3 is related to 1, 3 is related to 3. And down the last row, 4 is related to 1, and 4 is related to 3. And once again, we should check and make sure that we've got 9 ordered pairs since we had 9 edges and 9 ones. 1, 2, 3, 4, 5, 6, 7, 8, 9. I did not skip anything. Okay, so that is a good check. All right, so that does it for section 6.1. That is the representations for relations. I'm going to go ahead and stop this video now and do a separate recording for section 6.2 so that if you ever need to go back, it's easier to find the particular video that you want to watch.